Welcome to the video on Ksp. We'll be discussing Ksp, which is referred to as the solubility product, and solubility, how they're different and how they're the same. Let's start with what is solubility. Solubility is a number. It's the maximum amount of solute that will dissolve in a given quantity of water. We represent it in the units of moles per liter, i.e. the given quantity is going to be 1 liter. This is the solubility for calcium sulfate. So if I have 1 liter of water and I add 4.9 times 10 to the negative third moles of calcium sulfate, that solution will be considered saturated. If I add more, it won't. It's important to remember, though, that this ratio of solute to solvent remains the same no matter what size of volume of solution I have. So, for instance, if I have 2 liters of solution and I add double the amount of calcium sulfate, it is also going to be saturated. No matter the quantity of the solution, it's going to be the same proportion of solute, the thing I'm dissolving, to solvent, in our case most of the time water. Next, what is Ksp? Ksp is the solubility product. So Ksp is going to be the equilibrium for any sort of solubility situation at a given temperature, of course. So we describe the solubility product as the product of the dissolved ion concentration raised to their coefficient. I will show you that in more detail. Let's start with calcium fluoride. When I take calcium fluoride and I dissolve it, I'm going to get 1 calcium ion for every 2 fluoride ion that dissolve. So the Ksp expression of calcium fluoride takes the concentration in molarity of calcium and multiplies it by the concentration of the fluorine in molarity squared. And that gives us the equilibrium constant for this compound at a given temperature. And in this case, the value is 4.0 times 10 to the negative 11th. You'll notice the Ksp values are super small, so that's normal. Don't get freaked out by it. The other thing to know is that if you look in the back of a textbook, the Ksp value is the value you're going to find. You're not actually going to necessarily find the solubility of a particular compound. So the next question is, how do we use Ksp to find solubility or use solubility to find Ksp? These are the initial tasks that you'll be asked to do with the solubility project to be able to solve problems in this arena. There are going to be 2 kinds of calculations from Ksp to solubility. The first is this case where we have a 1-to-1 mole ratio. So for every one of your positive ions, you have 1 negative ion. And the second case is when your concentrations aren't equal between the 2 ions, because this complicates the calculation of the Ksp ever so slightly. So the way this problem might look to get from Ksp to solubility is you might be given the Ksp value for a particular compound and then asked to calculate the particular solubility or the concentration of either of the ions in the solution. Then our other form will be starting with solubility. So you might be told that you have a 5 molar solution of one thing and be asked to find the Ksp. So it'll be a much smaller number than 5 molar because that's not a partially soluble thing, but you get the idea. You'll be given a concentration and you'll be asked to find Ksp. All right, let's dive in. We're going to do 3 examples in the order from the other slide. So here we have copper 1 bromide has a measured solubility of 2.1 times 10 to the negative 4th moles per liter. If I'm given solubility, what is my Ksp? Step 1, write the formula for the compound given. Step 2, set up your Ksp expression. So in this case, we're going to write Ksp equals, and then because both of them have a 1 subscript, we're just going to take 1 concentration and multiply it by the other. No need for exponents or coefficients. The next thing to do is to determine the individual ion concentrations. So when I think about copper bromide, I know that for every 1 copper bromide, there's going to be 1 copper ion in solution and 1 bromide ion in solution. So this solubility will be the same as the individual ions concentration. The solubility being equal to the individual ion concentrations, I can simply plug the solubility into my Ksp expression, and then I multiply. you should get a final answer of 4.0 times 10 to the negative 8th. Pretty simple, right? Now let's complicate things, shall we? Problem, we have bismuth sulfide that has a solubility of 1 times 10 to the negative 15th moles per liter. You can see here, when I add bismuth sulfide, the solubility is no longer going to be equal to the concentration of the individual ions. As you can see here, if I have 1.0 times 10 to the negative 15 moles added, that means there are going to be twice as many moles of bismuth and 3 times as many moles of sulfur added. So I need to take the solubility and multiply it when I add it to my Ksp expression. I got a little ahead of myself. I forgot to mention that when we write the Ksp expression, the 2 that is the subscript in this formula becomes a superscript or an exponent in the Ksp expression. So a 2 here goes here. Now let's take the solubility, increase it by the factor that we have determined based on the number of ions produced, and plug it into our Ksp expression. Ta-da! Okay, so once again, I want you to note that we have an increase here with the exponents, as well as this number being larger than the solubility. Now it's time to calculate. Plug it into your calculator, see what you get. Your answer should be 1.1 times 10 to the negative 73rd. Remember earlier when I said not to be afraid of the tiny numbers? This again, this is a correct answer. Yes, it is tiny. Stick with me, we've got one more example to go. In this problem, we are given copper iodate and its Ksp. We're being asked to solve for the solubility. We're going to set up our Ksp expression with the copper ion concentration, the iodate ion concentration, and then raising that iodate ion concentration to a power of 2. Then I've set it equal to the number I've been given. Then I need to figure out what to put in these. And what it's going to be is the stoichiometric relationship between the ion concentration and the solubility, which really means that if I add 2 moles of copper iodate, that means I'm going to get 4 moles of the iodate, right? So that means that if my solubility was 2, my iodate concentration is 4, so I'm going to put in a 2x for the concentration of the iodate. Do we see how that works? So the copper is going to have the same concentration as the solubility, so it's just x, and the iodate is going to have double the concentration as the solubility, so it's 2x. And we're not going to forget to raise it to a power of 2. Then the very last step is algebra. Just solve. On the off chance that you're having a moment and you can't quite remember how to do the algebra, I have first distributed the exponent, so 4x squared. Then I multiply it all together, and I get 4x to the third equals 1.4 times 10 to the negative 7th. I'm going to divide by 4 and then take the third root of the number I get on the right side. Then my answer is 3.3 times 10 to the negative third moles per liter is the solubility of copper iodate at 25 degrees. It is important to note that here I have used an x, but more often than not in textbooks you will see the x replaced with an s, so just know that they're the same thing. I just use an x because it looks more familiar. Okay, I'm going to leave you with a question to reflect upon. How are Ksp and solubility different? How are you going to remember which is which? Because mixing those two up is a common occurrence, and it's good if you can keep them straight. Thanks for watching. Bye!